We don't want your kind in Beverly Hills. Now move it.
You wouldn't talk so sassy if I had my gun.
I hope you like them.
Well, there's nothing to like about them. Overalls are overalls, and these aren't overalls.
Uncle Herman, I'd like to have you meet my date. This is...
American fighter bombers flew 230 strikes on North Vietnam, mostly in the southern part of that country.
Hold it there. It's looking good. 110.
At the very beginning, before we started Walleye, we had looked at some bomb damage assessment pictures from Korea. And you can see a bridge standing there, and the whole countryside around is pockmarked with bomb craters. An attempt to take the bridge out. That was part of what led to, we really ought to be able to do something better.
It was really a leap forward, right out of the box. What else was there that even came close?
The pursuit of precision, in a broad sense, has been an essential aspect of warfare since man began throwing rocks. The evolution of ever more powerful projectiles made greater precision, beyond best-guess ballistics, even more essential. By the end of the Great War, the advent of the aircraft had led to the obvious application, and the pursuit of precision took on a new importance. The concept of aerial bombardment became firmly fixed into the concept of combat. But precision strike left something to be desired, to say the least. Once released, from rack, hook, or hand, the bomb followed a more or less ballistic course, depending on its aerodynamics, release speed, wind, turbulence, temperature. But that hardly slowed down the visionaries. The promise of aerial bombardment was pursued and demonstrated, much to the consternation of the traditionalists. And a measure of precision was obtained, in close and without opposition. By the opening of the Second World War, dive bombing was being exploited to good effect. But it was not exactly precise, and not very good against well-defended targets. Not very good at all for the pilots. But in a conflict in which entire cities, indeed whole societies, became targets, saturation bombing, carpet bombing, became the standard substitute for precision. Technological advancement allowed great improvements in precision, but a dumb bomb was still a dumb bomb, and a single factory complex might cost a whole town. Technology aided the defenders, too, and bombing became an increasingly risky venture. Even with 1,000 planes dropping untold tons of bombs, some targets remained elusive.
In World War II, we moved up gradually. The largest bomb we had in our inventory at the end of it, the conventional bomb, was a 42,000-pound general-purpose bomb.
The Allies built those blockbusters to go after hard targets. Big bombs, but not at all smart ones. The clear solution to the problem of precision always came back to putting the direction, the guidance, in the weapon.
They were thinking about using them on some of the flak towers in Germany, and also thought of using them against submarine pens. But they were talking 20,000 pounds of explosive aboard a cleaned out B-17.
Pilotless aircraft had been attempted almost as soon as there were airplanes and radios in the same vicinity. Not only were these early attempts plagued by unreliable hardware, ill-suited for banging around in an airplane, these putative guided missiles required a controller, a pilot, who could maintain line-of-sight control over the device, flying it from the ground, and when the radio gear got smaller, from the air. The major breakthrough in TV's evolution came when the original mechanical scanner was replaced with an electronic system. As electronics advanced during the 1920s, Vladimir Zworykin and Philo T. Farnsworth demonstrated electronic imaging tubes, with Zworykin's iconoscope leading the way. By the late 30s, experiments in airborne TV transmission were being conducted using an iconoscope camera. The equipment was big, heavy, cumbersome. Even in the Ford Trimotor it was tested in. But the successful demonstration promoted efforts towards smaller, lighter television hardware, and for further development of more advanced camera tubes. As a new war in Europe was building, new urgency was applied to adapting the amazing new technologies of the era toward more deadly ends. Radio was still a wonder, and radar was a secret. A lot of people knew that television existed, but the majority hadn't seen it. The arrival of television in the average American home had been put off by Pearl Harbor. Wartime priorities took precedence for its proprietors. The war, inevitably, provided impetus for more experimentation. And in 1940, several programs were initiated to adapt the rapidly evolving technology of television to military needs. By 1943, many people felt that TV was sufficiently advanced to play a role in the defeat of the Axis. Zworykin himself suggested that a flying torpedo with an electric eye be developed. Still a command-guided device, but with the TV advantage, he hoped, of having a picture of the target from a bit farther away. Both the Navy and the Army had already begun investigating television technology for airborne fire control, remote control, and weapon control. The primordial guided missiles in the works included small, remotely piloted gliders, large bombs with controllable tailfin kits attached, and worn-out bombers with TV cameras. Stripped down and loaded with explosives, old B-17s had the new television cameras mounted, with the idea of precision strikes against particularly hard and particularly difficult targets. The concept showed promise, but the rigid camera mounting was unsatisfactory, and a live crew had to pilot the so-called Weary Willie to a point where a remote operator, either airborne or on the ground, could take over, and the crew could bail out. One of the better applications of TV during the war was another drone development. The TDR-1 was the first viable weapon to be built around the camera. The small, carrier-launchable assault drone was used effectively in the Pacific in 1944, but it was withdrawn before the war's end. An attempt at a true TV missile was made with Robin, a glide bomb airframe with a camera to provide its radio controller with a target picture. But the limitations of television technology prompted the shift to the radar-controlled Pelican and Bat projects. Neither Bat nor its cousins, Azon, Raison, Felix, Moth, various GBs, saw more than limited application, and most were command-guided. Someone had to watch it, had to drive it, had to remain too near the target. The bombardier wielding the joystick that guided his Azon toward a particularly valuable bridge was likely to encounter some potentially deadly opposition to his efforts. With television promising a picture, television promised distance. In a war of technology directed against technology, precision of a sort directed the bombers and released their bombs. Gyroscopes and jet vanes shaped the ballistics of terrifying long-range rockets, and almost any conceivable technology was applied to the pursuit of precision. Pigeon guidance hadn't quite been abandoned by war's end, and bombs were carried by, guided by, trained dogs and terrified bats. And desperation made for even more sinister guidance schemes. And barely technologically feasible schemes for their undoing, with the abandoned attack drone as a test target.
We read science fiction books and we try to make some of that stuff happen. Some people would tell you that satellites are up there because of Arthur C. Clarke's books that put them up there before there was a way to do it. So it's pretty easy once you have TV on the market. If you could put that in the air and figure out a way to use it, you could see what you were tracking.
And TV did hit the market after the war. Slowly at first, but with ever-increasing speed as television began moving from appliance store windows into America's living rooms. The technology of television during the 1940s was still generally too primitive for most military applications. Vacuum tube technology, although advancing daily, still made for large, heavy, and hot hardware. By the end of the decade, though, the basic component of the electronic revolution that would overthrow the vacuum tube was already being demonstrated. The implications of the transistor's arrival on the scientific scene were profound enough that Bell Labs had briefed the military before it called a press conference in June of 1949 to reveal the breakthrough to the public. But that radical technology was still some years away from being able to survive, let alone function reliably, in the environmental extremes of the missile regime. The opening of the 1950s brought America into another war. Euphemistically described as only a conflict, the Korean War saw the secret wonder weapons of a mere half-decade before, jets and radar and rockets, become the daily standards of combat diplomacy. Airborne fire control and rocketry were dramatically improved, but any degree of precision still required up-close attack, and the new radars made the new aircraft increasingly vulnerable. A few bad airframes were fitted with television cameras in the hope of providing precision from a distance. But most early guided missiles remained, of technological necessity, command-guided, with an operator too close to the target, and radio control was wide open to interference, and increasingly, jamming. Getting the man out of the loop remained one of the primary goals of guidance development. And getting the target while missing the town around it became increasingly important in a war-weary world.
As a country, we have been concerned about collateral damage through the whole thing. We target very carefully in choosing the weapon we're going to use to do sufficient damage to the target of interest and very little collateral damage outside of that.
Once you start down the path of guided weapons to where you haven't had them before, a whole world opens up in front of you. Guided by what? What can we use for sensors? RF is an obvious one to look at. IR, if you have IR detectors, is an obvious one to look at. Imagers, if you have imagers, are obvious ones to look at.
They looked at everything. RF and radar systems, command-guided, beam riding, active and semi-active and passive IR, the heat seekers, even before the technology would support them. And there were experiments with visible spectrum beam riders, missiles that would fly down a searchlight beam, not likely to be popular with the pilot who had to hang around and drive the bomb, or shine a spotlight on the target. Television's rapid evolution during the 50s was driven by both defense and commercial applications. Programming expanded exponentially, and every family wanted the latest equipment to get it. And every service wanted the latest equipment to guide its weapons. The arrival of the transistor opened the door for the greater range of environments, better stability, and miniaturization required by guided missiles. With that new technology on the horizon, experiments in TV guidance and fire control, ranging, and surveillance were accelerated during the early 50s in the military labs and throughout industry, including an effort that would result in the first successful demonstration of an automatic tracking television guidance system.
It was amazing how much we stayed with sort of a beam rider guidance for a while. Then we sort of stayed with a pursuit system. And finally, we did wind up with things that could handle a proportional navigation, which took you out of the problems that you had in the others. The others always tended to wind up calling for infinite accelerations at the end of the flight.
You would like to be able to just launch it and forget it. And that was the original Walleye philosophy, and which was difficult. That made it really hard on the early designers.
This friend of mine that I worked with in Sidewinder named Norman Kay was a TV nut, which was interesting at that time, rather far out. And he had in his folks' residence in Los Angeles an early iconoscope camera which he had built. He was telling me how he was getting this iconoscope camera going into all of the technical details and so forth. And then he mentioned that he did a funny thing that it occurred to him that he could build a little circuit into there that would put a little blip in the picture, and he could make a little blip track things that would move in the picture in one dimension only. And he said he breadboarded this, and he came bustling up to the 4th floor, I think, one day and said, it actually works. This little tick attached to someone's head, and as they walked down the street, it tracked it.
Woodworth mentioned the funny thing to Jack Crawford, another member of the Aviation Ordnance Department who had also been involved in aircraft fire control system development. They were among the young engineers at China Lake who were starting to look into air-to-surface guidance solutions. And both were interested in this new technology of television. By 1957, TV in some form had been around for more than 3 decades, and the iconoscope camera, which had made a name for Vladimir Zworykin, had been demonstrated by the end of the 20s. But the technology supporting the television revolution still showed more promise than prospects. The at best limited results of the World War II efforts to adapt TV technology to the guided missile had little deterred the pursuit of precision using electro-optical devices, and every advance in the state-of-the-art was explored and exploited. By the early 1950s, interest in adapting this modern-age marvel was growing apace. Government, academic, and industry labs explored TV for range finding, guidance, and fire control. But the ultimate target, as it were, was autonomy. Getting away from command-guided missiles that required someone to hang around the target and drive the weapon in. Creating the launch and leave capability that would combine precision and standoff with survivability. In 1951, Fred Alpers and his group at the Naval Ordnance Lab, Corona, began the development of an automatic contrast tracking TV guidance system, Avocet.
He is credited with developing the first video imaging seeker with some kind of a tracker to go with it. That sets the stage for a video tracker, probably before you really have practical hardware to go build one with that you can fly.
Avocet was a product of its time, large and mechanically tricky. But the Corona effort provided another step in the evolution of television guidance, a step nearer autonomy. By the time the China Lakers picked up the camera a few years later, 41 million American homes had television. And the state of the electronics art had evolved to a level that would support what was still quite a complicated proposition. To build on the efforts of the 1940s and early 50s, to create an auto-tracking TV guidance system, to build it on a moving platform, and to convince someone to fund it.
It was, kind of just a chance convergence of things. Some people at Corona had come up with a television tracking system, realized that, yeah, that works, but it requires non-standard scan on the TV, and that's going to complicate things. So we set about to devising one that could use standard scans, and concluded that, yeah, by golly, that works. And just by chance, I had bought the 3 volumes of, they're thin books, by RCA on the history of television. And one of them was history of television in World War II and the efforts to build a TV-guided bomb then. And it was really evident, looking at that and current technology, where the holes were, that there were things they did that were really disadvantageous. Like the TV camera was hard-mounted. Well, if it's hard-mounted, then it's got to have a fairly wide field of view in order to be able to see the target as the missile maneuvers. But that means you can't see very well. And we concluded you need to gyro-stabilize the camera and have a much narrower field of view. And with a number of adaptations like that, we came up with what looked like a workable scheme. And talked to management, and they gave us some discretionary funds.
Although this was the start of what would become the Walleye Development Program, it wasn't the start of the weapons development per se.
We learned how to build TV stuff that could go into a missile.
We did develop a camera system that was very small and compact and fully solid state, and no vacuum tubes and all that jazz, which was not so easy to do in '59. And we were developing one that would be appropriate because there was nothing available. The things that were available on the commercial market had vacuum tubes in them, and they were big, clunky things. And we had to develop a television camera that could be mounted in a gimbal.
And for essentially 2 years, we just played. And we flew it around in airplanes and looked at targets in the vicinity. Awful lot of people here don't know they were looked at as possible targets. You look out the window from the 4th floor and you could track cars going down the road and so forth. And all of that, we concluded, yeah, it'll work.
What they called playing, the station called exploratory and foundational research. Famously, many aspects of Sidewinder's early development also drew upon in-house funding to move the project forward against the will of an often intransigent bureaucracy.
Well, if it wasn't for Sidewinder, Walleye would never have been funded because we started out with no funds.
Walleye stole a lot of my money the original Walleye was a lot of Sidewinder money in it. They'd put you in jail nowadays for doing that, but then we could get away with it. I'd pay some, and we wouldn't transfer funds. I'd simply pick up some of their time cards and that kind of thing. Well, he did it with my permission, certainly.
Walleye had a lot of Sidewinder people in it, too. Sidewinder experience and money and AOD corporate culture helped shape the early program. But once the playing was done, the TV project would establish its own identity. And the atmosphere at China Lake was conducive to the broad-based exploration needed to support it.
We had freedom. to pursue ideas. At the time when I first came here, we seemed to be funded and free to do the work.
That's why it was the best place in the world to be. I had my hobby, gyros. I had the free hand to do with the gyro as long as I could make it work for them.
Laboratory leadership tried to ensure the physical resources, too, to support the intellectual.
If I needed a brand new integrated circuit that just came out on the market, at the time, I would simply call up a guy named Bob Green in procurement on the telephone and say, Bob, I need one of these, and it would be on my desk within 2 weeks. And we all know that approach changed, but then you probably can't really let a bunch of maverick engineers run around doing that very often, because you'll break the bank. We'll buy every play toy out there. But at the time, solid state technology was advancing so rapidly that if you didn't do that, your design would be obsolete before you ever got it finished.
I think it really goes back fundamentally to our management and the fact that our top management was top scientists and engineers who understood development and what makes it work and how it gets aborted.
At first look, when you don't know, you think that you can just strap down a camera and use some fins and fly.
The other thing that was very important was to have the camera system gyro stabilized so that it was free from the movement of the body that you were guiding.
The necessity of a gimbaled seeker had been well demonstrated in early systems in which the camera was rigidly fixed to the airframe.
So any motion of the airplane could look like a change of the target, so that you were just strapped down, looking out the nose, and if the airplane took a little wiggle up and down, the picture wiggled.
By the end of the Second World War, the technology that would enable a television camera to ride a gyro was only about a decade away. And the expertise needed to put the two together had been perfected at China Lake with the development and evolution of the Sidewinder seeker.
Jack pointed out that the way to get around the problem that BAT had was to gyro stabilize the camera so that you could measure sight lines. That was Sidewinder. Then the signals required to process the gyro would be measures of sightline rate in space, and we could apply the same guidance that Sidewinder utilized, the so-called lead pursuit or proportional navigation.
If you can steal somebody else, do it. They've gone through all the hassle of figuring out how to make whatever it is work. So no need to repeat all that.
And what the Walleye team couldn't steal from other station projects, it developed. Improved and downsized video cameras and new TV technology, novel gyro platform schemes, and tracking and video processing circuits, the ongoing revolution in electronics, the evolution of solid-state components, allowed a new level of sophistication in a much smaller and much more reliable package. And the designs matured as the technology progressed, although it would still be many years before solid-state imagers became available, let alone anything approaching a microcomputer. Much of the advance of TV technology was worked out in hand-drawn plots and calculated with something called a slide rule.
It was amazing how much was accomplished in a short period. And particularly in today's technology, you look back and say, man, they did that with slide rules and hand calculations and the occasional Marchant mechanical calculator.
I did things that kind of off the wall that you don't find in any books.
The mechanical design for the missile presented unique challenges as well.
I had to be able to couple or to connect electronics over the pivot points in the gimbal system. I needed to know the moment near zero torque. Found out about an outfit 20 conductors in this thing, and it's a gimbal mass. And I come across the pivot points with those this thing, and it's only a 1/16 of an inch thick for the Vidicon to pass through the bearings. And a very stable unit. Being optical, it had to be. And for torque motors, I took the same configuration as torque motors that we had in Sarah, and this is the rotor out of one of the Walleyes.
Many of those innovations directed at Walleye would also set new standards for television in general.
The zero input impedance video amplifier, which overcame a lot of technical problems, and subsequently everybody used it. The Navy should have gotten a royalty on that, but they never did. And we also developed the first practical automatic electronic light level control for television cable of that sort. Subsequently, everybody else used that same scheme.
Perfecting a targeting scheme and a method for defining the target within the TV picture were the final keys to the guidance system.
If you look at something, you see that by contrast. Everything in your field of view, you see because of a contrast between that object and its surroundings. And so you look at the television signal, and the signal is nothing but a signal representing how bright or dim a spot is in the scene. And what we did was take that signal and differentiate it. Differentiating gives you the rate of change of the signal. And that's essentially the contrast at that point. And we rectified it so that it didn't matter whether it was a positive or a negative contrast. And the only trick is you don't want something nearby to have more contrast to grab it. But if you restrict the area you're looking at to a small area, then you can do that most of the time. A small gate that is displayed on the pilot's monitor so he can see what he's locking on the target.
And that was innovative, to try to figure out how to take apart the electronic stream of data you get from a Vidicon and figure out what is a target. When you look at it on an oscilloscope, you don't really know unless you've been in this business. You can't look at that and say, that's my target right there. Now, how can I build something that can always recognize that once I stick it on there?
The next big conceptual development in this whole business occurred very suddenly. Jack had always said, we ought to make the television track electronically by itself, because the original concept of this was that in this little gated area we would develop electrical error signals that would go to move the gyro. Other people had tried the same sort of thing, as we found out later. And they came a cropper on it, it didn't work. Jack had said, let's make the television track all by itself, with the gated area independently moving and tracking by itself. That was what made that guidance system practical. It was a two-loop tracker, actually. It had an electronic tracker that moved the little tracking crosshairs that the pilot could see. It would do that electronically. And then the gimbal would, in essence, track the position of the gate. And it formed a dynamically stable system for which error signals could be taken easily and used to control the aerodynamic fins, and at that point it was a Sidewinder.
It wasn't a Sidewinder. It was the first truly smart bomb. And by the standards of the early 60s, it was truly revolutionary.
The approach Walleye took was to use a small gate. That means that there would be, with electronic timing, define a small area in time and say what I position in there is my target. I will look at the edges of it and I will stay on them. Okay, it's not smart enough to know that a bridge is a bridge, or a car is a car, or a tank is a tank. It's not that smart, especially then. But it can know that an edge is an edge and try to stay stuck on that edge.
In the early versions of the weapon, the pilot had to aim it, airplane and all, to put the target in the gate and lock on the seeker. But because it was smart enough to stay stuck on that edge, the pilot who dropped Walleye could not only be highly confident of putting the warhead through the correct window, he could be well out of harm's way by the time the weapon hit.
There's no need to waste cost and weight and space with a motor if you can't see any farther than you can glide already.
Frankly, Walleye to this day remains an enigma to many people who really weren't familiar with just how capable it was. It was always pointed out as Walleye had a range of X. Well, when you get into the depth of it, it was much more than X miles. It was a very capable system.
The experience base available with glide weapons also influenced the decision to choose an unpowered platform.
When we had originally started talking about television in a weapon, it was intended that we would do something like the bat and use a data link to control it. The later successful operation of the electronic tracker threw the data link concept out, and we forgot about it.
The data link wasn't forgotten for long. But in the meantime, there were at least a couple of other problems to solve. The actual airframe design, for one thing. With exploratory funding secured and the seeker design well underway, another AOD group began the analysis of potential aerodynamic configurations. Wind tunnel and sled testing at China Lake started in the fall of 1960. And the combination of computer simulation and experimentation yielded a tactical configuration that was drop tested in May of '61.
Walleye has very small wings, relatively speaking. You know, as a glider, you'd normally expect it to have, you know, real airfoils, real wings, something that looks more like an airplane. Well, Walleye does not. It has 4 highly swept, very short wings on it that aren't terribly efficient for something that has no power. And so there was always a question of just how far could you pull Walleye angle attack before things really turned sour. In the wind tunnel, and Walleye did some excellent wind tunnel work, they spent money wisely on that one to really understand the aerodynamics of that configuration.
Another issue was letting the weapon talk to the airplane, and vice versa. Integration avionics could be complicated, but following China Lake's well-proven model...
Well, that's pretty simple stuff, because you need a TV monitor and a control that allows you to lock on and launch. And so there wasn't really much to that.
Simple, perhaps, but it still required shoehorning some extra controls and one of those heavy tube-infested TV monitors into the little A4 Skyhawk. Of greater significance was weapon power. In an era when batteries were still heavy and generally short-lived, the obvious answer for missile power and actuator pressure was the tried-and-true China Lake one.
Since we had already stolen the sightline rate measurement scheme the Sidewinder used, we'd stolen the torque balance actuators scheme that it used. Next thing was to steal the gas screen.
When we started out, the obvious thing to do was to use a hot gas power source with a high-speed turbo generator and then use the gas from the generator also to run servo actuators for the fins. But the development of the grain for the hot gas generator did not go well. You know, Sidewinder's a fairly short flight time, and Walleye could fly for a minute and a half on a long launch. And that meant you had to have a large grain that would hold up, not have junk that would foul the ports and so forth. And it just got to be troublesome.
Another option was just becoming available. One of the things that makes Walleye Walleye, aside from that huge staring eye on the nose, is that mysterious little propeller thing on the tail. Stepping aside the Sidewinder model, the Walleye team adopted a recently developed ram air turbine generator, the RAT, with its little airstream-driven windmill, and a hydraulic servo system for maneuvering.
Very clever arrangement because you didn't have to carry batteries. And you only have that thing operating when it's in the air.
However, the RAT wasn't ready when the first guided test round was assembled in early 1962. So the proof-of-concept Walleye was loaded with rather primitive thermal batteries and a jerry-rigged pressure bottle for its modified Sidewinder actuators. The first test was inauspicious, a victim of a minor mistake.
There was a mathematical error in the roll control loop, and it was hooked up backwards. So instead of roll stabilizing, it spun.
It was the second test, on the 27th of November 1962, that made the program. Like Sidewinder, like Shrike, the first all-up test weapon had successfully demonstrated its guidance concept, and done so using makeshift supporting hardware. In April 1963, Knott submitted a technical development plan to the Bureau of Naval Weapons, and Walleye was official. Impressing the Director of Defense Research and Engineering with the weapon's accuracy helped push the program along. But the threatening conflict in the jungles of Southeast Asia provided an even greater impetus for the pursuit of precision.
From 1962 probably through 1969, it seemed like it was involving almost every weekend and nights in the whole works. It was obviously something that was necessary because the Navy had nothing that would do what this particular system would do.
Even as the war in Vietnam was becoming the staple of the nightly news, Walleye was not the station's highest priority, nor was it the Navy's, but getting Walleye out of the desert and onto the deck was a priority.
It was fully realized, even by somebody as unpolitical as I am, that if you let it lag, even for a little bit, it would die. And so that's why you had to have constant progress.
The China Lake team built and tested, refined, corrected, tested again, improved the aerodynamics, fine-tuned the electronics, replaced the original RAT. And while they were solidifying the basic capability weapon for the fleet, they were also investigating and designing the upgrades and advancements that would follow it into the pipeline and into combat. As the test series continued at China Lake, the station engaged the Naval Avionics Facility, NAFI, for production engineering tasks. NOL Corona was assigned to develop the fusing. A two-stage pressure probe-initiated system emerged that satisfied operational and safety requirements. And in 1965, NAFI was assigned by the Bureau to conduct pilot production. Although the project was delayed significantly by Washington decisions regarding NAFI's role, and problems plagued pre-production rounds which had to be reworked with the help of the Naval Missile Center, which was conducting the technical evaluation, the design was frozen in 1966, and delivery began of pilot production rounds for initial testing and in preparation for op eval. The first all-up live warhead Walleye was launched at China Lake 22 April 1966. The shot was perfect, and the weapon completely demolished its 18-inch thick reinforced concrete objective. The X-5 initiated OPEVAL, the operational evaluation, in June of 1966. Fleet introduction had already begun when live weapon drops began in November. Even with the delays in technical evaluation and production, fleet training was accomplished quickly, and Walleye was officially declared operational, although OPEVAL was not yet completed, on 12 January 1967.
This went from the first successful one in late 62. You had a combat use in 67. You can't do that anymore.
Some of the more interesting shots were, the pilot deciding which window of the Hanoi power plant to fly the missile through. And it was quite successful attacking coastal caves, which had been very difficult to attack, and bridges, which is one of its primary targets.
I was in VA-212, and it was 1966, and we were on a pretty fast turnaround. We received the word at that point that we were going to be introducing the Walleye into combat. For that Walleye cruise, the initial Walleye cruise, we were shifted over to the Bonhomme Richard. And so that's what we deployed with, the Walleye. That would be in 67. I think it was in January, if I'm not mistaken.
And we were the first, we did the combat introduction of the Walleye. And it was one of those things that just happened. I mean, it was the luck of the draw. We had new airplanes at the time. We had new Bay-4Es, and I guess they figured with the timing and the aircraft and everything worked.
It was more than combat introduction. With production issues having delayed technical evaluation, operational evaluation wasn't complete by the time the weapon was conditionally approved for service use. It was, in effect, combat OPEVAL.
We did the transition into the Walleye during our turnaround, and then we went out in the Bonnie Dick, and that's when we actually got into it. And it was combat evaluation, combat introduction. And we had a team in the squad. We only had 6 people initially that were on the Walleye team.
6 of VA-212's pilots would evaluate the weapon and pass on the training to the rest of the squadron. Homer Smith, the skipper, whose destiny was woven in with Walleyes. And Dick Thomas, Bill Green
and Mike Cater, and Steve Briggs. Bernie Smith was a new input to the squadron. He was selected because I think they wanted somebody without previous cruise and combat experience in order to look at the compatibility of the weapon system with a certain level of training.
Initially, the training was sort of limited, and we didn't have enough weapons to really go around. So there was really a team that was developed in the squadron until we got the process down, and then we started expanding. And the initial bunch, there were 6, and we called ourselves the Succulent 6 because we were never going to live very long because of the envelope that we had to fly in. And anyway, we had patches made up and just for those 6, the Succulent 6.
It was irreverent and, and stupid, and that's what sold. We had a patch made, and it was kind of a sunburst, as I recall, with a missile in the middle with a big eye on it, and it said Succulent 6.
Pilot and maintenance instructors had been trained at NAS Lemoore with China Lake and NAFI support, trained quickly and with no live drops of the weapon. Walleye arrived aboard with basic documentation, delivery specs and the like. However,
I think there were some charts that somebody had probably put together, and were probably fairly accurate, knowing the work that China Lake did on those kind of things. But since there was no operational information provided, we didn't know what kind of targets were best, or which, what was the criteria for hitting certain targets, you know, and there was an awful lot of that information that we had to develop. And as a matter of fact, to be very honest with you, an awful lot of that stuff fell in my pocket.
the 6 and the other members of 212, with support from VX5, came up with procedures to meet the requirements for evaluation and fleet introduction. VX5 had taken the weapon out to sea in November for cats and traps and preliminary training.
Tom Taylor came out when we did the introduction to Walleye, because he had been one of the project officers on the Walleye program at China Lake.
I think it was a good idea to do it with a combat squadron, because not only do things happen faster, you can reveal severe weaknesses, but you can also reveal good success in a high-stress environment, and you don't have to. It doesn't have to be a real canned scenario. Sure, everything was highly planned, and sun angles and dive angles, and you know how to approach the bridge or whatever the target was, or the warehouse, and do we want it to fly in a window? Do we want to go for this corner? And there was a lot of research done for figure out what the aim points were best, what delay belongs in the weapon, and you know, does it detonate as it goes through the glass, or does it go through a door, or you know, so the delay on the fusing and stuff was important.
It was a great enhancement to our capability, and we saw that right off. But it was new and different, and it was a thing that, you know, nobody had ever had any experience with before or anything like it. And we approached it very seriously because we could see the advantage to it. You know, there were disadvantages that we also saw, but the greater advantages was, instead of going back 12 times to a target, you go once and you got a good chance of knocking it out.
You know, it was really a leap forward, right out of the box. I mean, what else was there that even came close? This thing, you know, it had a standoff to it, had a lock, you could get out of there. The accuracy was extremely good.
Seeing its potential for minimizing collateral damage while maximizing pilot survivability, the operators were quick to embrace the new weapon. The accompanying addition to the pilot's workload was minor and worth the investment.
It amounted to the fact you had to do a little bit more planning than a dumb bomb. On the other hand, it was probably well worth it, because this thing was so much better than dumb bombs. The only other thing we had was the bullpup. And the bullpup B was bad enough. Bullpup C was terrible. It you know, had a tendency to blow up in front of you after you launched it.
Bullpup was a remnant of an earlier era, command-guided like its World War II predecessors. And in contrast, it highlighted Walleye's advantages to the operators.
Unfortunately, even if you were 100% good at guiding that thing by hand, you were putting yourself right in the middle of the flak zone, and you had to come right down through it, and you couldn't break away. You had to stay with it. So it was not a popular weapon if you had any opposition.
Ironically, it would be that hang-around tactic that would be employed to help ensure that the tactic would no longer need to be employed.
I don't think we were directed to do it. I think what happened was that we were told we needed to get, you know, as much data as we could, and we figured that was the easiest and best way to do it.
The easiest and best way was far from easy. Combat evaluation in the absence of modern telemetry equipment. Walleye effectiveness was recorded by a pilot who followed the weapon from launch to target. Complicating matters, The video recording equipment of the day was neither widely available nor well suited to the rigors of flight. But backed up by the venerable 16mm motion picture gun camera, the technique produced some spectacular results.
The best film I got, I lost the video recorder pod. I mean, it went black. So all I had left was the Mopex. I didn't know until I got back what I'd actually seen, you know. Near Venn, where Bill Green is carrying the Walleye, and I was taking the film behind him. And it shows very effectively, you know, from the time he drops it until it hits, exactly the capabilities. And you can see the walleye all the way down until it hits the target. But the only problem I had was trying to stay behind it because, you know, I was reasonably close to him and the weapon's slowing down as it goes down, and I'm trying to slow down. And when you get to idle and have the speed brakes out, that's about as far as you can go.
This version of follow the leader was no game. Flying chase on the weapon was a potentially deadly pursuit. Not only was the enemy filling the air with flak and missiles, there was another distinct danger in being on the tail of a walleye warhead.
Some lessons were hard learned. The pilots quit following the missiles in after launch when, a long time ago, just before I came here, the weapon hit the target. It blew pieces of the target up in the air and plane ran right into it. We lost the pilot. So that was on this range. So like I say, some lessons were learned the hard way. In hindsight, you say, of course. Why would you ever do that?
We were told we needed to get, you know, as much data as we could, and we figured that was the easiest and best way to do it. So that's what we did. I made 6 passes on the Thanwa Bridge, and the Thanwa Bridge was a one-pass target. I mean, you did not stay there because of the circumstances. And I remember vividly telling the people that I was following that the shooting was getting much more intense each time we came around and made another pass. By the 6th pass, it was wall to wall. So, I mean, that was stupid, and we all admitted that. But, you know, it was also essentially a requirement, so we did it.
Well, we lost our skipper, and he's the only one. Had a few pretty well shot up. I had one torn up all around me. I came out of Hanoi with 3 different fires.
They did do as they were ordered, and the strikes against the Hanoi power plants became the stuff of legend. It was VA-212 and its Succulent 6 who first put weapons through the windows.
It was a very hostile environment down there, and it was far enough from the water. It made you very nervous every time you went in there. Because, you know, if you took a hit, you're pretty much there for the duration, because there's no way out. The first one was on May 19th of '67. It was targeted for 2 airplanes. We had 16 F-8s with us, 8 flak suppressors and 8 Meg cap. We had a very circuitous route in. We went in way south and went up through the karst ridges back and forth and around and came through a nice little valley in the last karst ridge on the way into Hanoi, and the first missile came and, you know, right over our heads. So the surprise element was less than overwhelming. They fired about 200 missiles at us as we came in there, and had at least 10 or 12 MiGs up because we shot down 4 of them and lost 4 of our F-8s on the mission. We were going way too fast because of the circumstances, and I saw his hit down in the end of the complex in an administration building. Mine, I didn't see where it hit, partially because I had a MiG shooting at me, and it was making me a little nervous. In the meantime, my Walleye goes in, and we found out later it hit the boiler house and blew out the side of the boiler house. So that was the first one. Then we all came back, other than the 4 that we left there. On the 21st, we went back again, In that time, the defenses, the weather was perfect, the defenses were marginal. They didn't fire more than half a dozen SAMs at us in the whole trip. We saw no MiGs, and we put 4 into the, 2 into the boiler house, 2 into the generator hall, and shut the plant down, which pretty much made headlines throughout the country that the city of Hanoi was without water and power because of a strike on the power plant. So that one was a great success, and it probably made the Walleye what it later became. I mean, it was proven at that point. Then later on, that fall, probably in July or August, when Bill went in, and with another 4-plane strike and shut it down again.
We hit it okay, and but we didn't know how much damage we did to it. The only thing we got was I guess it was a Japanese newspaper. Next day or a few days later said that they had an article, and they're dining by candlelight in Hanoi tonight.
Those downtown strikes were also responsible for 4 of the 7 Navy Crosses and the only Medal of Honor awarded to A-4 pilots during the war.
We did the first 3 attacks on the power plant. That was Homer, Smith, and me. The 19th, we went into Hanoi, and the 20th, we went to another power plant, and that's where Homer was shot down.
Had 4 aircraft, and skipper got hit. And he released his weapon, okay, but then he got hit just about that time.
He ejected very low and very fast, and we saw him walking on the ground, but was later declared dead. We figured they probably killed him.
The power plant raid set the standard for precision strike. Maximum target impact with minimal collateral damage. And compared to multiple minimally effective strikes, greatly reduced pilot exposure.
Well, it worked for us, and I know it worked later on when the guys went downtown again with it, that the satisfaction of really seeing a material confirmation of your efforts, the lights don't come on, is a fantastic feeling. I mean, you really can boost morale with something like that, not just for the people who are doing it, but for the whole forces who are out there trying. I mean, we used to talk about going to bomb the suspected rock and leaf storage area because we'd go back to the same target over and over and over again. And the joke was because you wondered, how are they picking out these targets? How do they decide what bomb damage assessment is? I got 7 leaves and 4 trees knocked down, and I made a 28-foot hole in the ground, which they filled in about 16 minutes with 50 men with shovels. And so you didn't see the evidence. It was, it was momentary, not like putting out the lights.
We used to spend a lot of test flights tracking the cement plant over to Tehachapi. It was a very good simulation of a power plant. If those guys only knew, we had a lot of video of the Tehachapi cement plant.
Walleye was designed for hard targets. Not just targets that were difficult to hit, but targets that were difficult to knock out. In the first phase of Opival, VX-5 shot boats, bridges, SAM sites, and train tunnels at China Lake and Point Mugu. But the targets chosen for Walleye's combat Opival would be another story. And those targets would shoot back.
Those were very, very specific, but there were enough specifics that they became a generic in their own little category.
And this was a new sort of conflict. Washington was increasingly directly involved, and the nightly television news showed every detail. There was less tolerance for the collateral damage and the aircrew losses of previous wars.
Carpet bombing is effective, but it covers an awful lot of ground and takes an awful lot of airplanes. we started on easy targets, little bridges in the Vin area down in the southern part of North Vietnam, and then we worked our way north as time went on and we got more competent with it.
They may have started with little bridges, more or less out in the country, but they ended up going downtown.
The reason we finally got into Hanoi is after the workup showed that the accuracy was very, very good. That's the first time they allowed us into the inside of Hanoi, because you couldn't afford to have errant bombs going all over the place, because it was an international incident every time that happened, because they always claimed you hit an orphanage or somebody down the road that you weren't supposed to. So we were very, very sensitive to those kind of issues.
They also took on the Samson barracks. Bridges large and small. And the notorious power plants.
We were able to go after not only buildings, but specific windows in buildings, which we thought was something pretty neat to do that. And I remember the first building that we went after in that category where we went for a window was the Samson barracks. And we were able to put those babies, I think there were 4 of them, right smack dab in the windows in those barracks that we wanted. And this was a substantial building.
And as to the selection of those targets, the operators had little doubt about the origins of the Walleye target list.
We had a number of targets that were given to us for the introduction of this thing. And these targets were dictated to us from on high someplace. I have heard that in some cases they were generally as high as McNamara. And in a couple of cases I would say that that's probably pretty accurate because they were inside of Hanoi.
And the targets came down from above, probably out of Washington, with a strong influence from VX5 and China Lake about what kind of targets, what you should be doing.
We were told it came right out of the White House, and we had no reason to disbelieve that. And the targets were, when they targeted the Than Hoa Bridge, we knew that was a loser. There was no way we were going to knock the Than Hoa Bridge down with 700-pound bombs. I mean, it had seen 2,000 or 3,000 bombs that were bigger than that. But they wanted to try it, and we put several on it in the same spot, and it didn't do much.
And all we did was leave black spots on some of the spars. And, we'd hit it right where we wanted to, but nothing happens.
The solution to that situation was already in the works at China Lake. The 850-pound warhead of the little walleye was soon to be eclipsed. But in the meantime, 212 would expend 43 walleyes during its tour, destroying buildings, wrecking power plants, and annihilating railroad locomotives. The combat Oppoval scheme was highly controlled by the aviators and the analysts involved.
Each one of those shots was analyzed and reported on. And I don't remember but maybe one that had broke lock that we know about and did not even come close to where it was dropped at, and maybe one.
At the same time, the Air Force evaluated Walleye on its F-4 aircraft, scoring 8 direct hits in 9 combat launches. The A-212 passed the weapon, praised its accuracy, and demanded more range and more warhead for the next round.
We got good information from China Lake always about what they were trying to do with the warhead and why they designed it that way.
Walleye's warhead was a special proposition, a unique linear-shaped charge product of China Lake's decades of energetics experience.
I'm really not quite sure why we came up with the original concept to try and develop a linear-shaped charge. But it obviously started with the knowledge of what a conical shaped charge can do and how you can direct the energy. We did a lot of testing. And we started off with developing a test unit that was just a single vane. And with that, we were able to decide what thickness of metal we wanted to use, what angles worked, what angles didn't work, and why.
The original Walleye's 850-pound warhead, carrying almost 500 pounds of explosive, was more than a match for most of the targets on its list, and considerably more deadly than even larger conventional munitions. The 8-point star pattern focused the energy of the explosives to create tightly beamed jets of energy and high-speed metal fragments.
That warhead concept was developed purposely to take out hard targets. That was the game. Dams, or totally blow up a big tank or something of that nature, bridges. And you could have a delayed fuse so that it would actually penetrate the target partway before it went off.
There was one test that we developed that turned out, I think, to be one of the main selling points for the linear shaped charge warheads. We had on the one side a 10-foot thick wall of concrete that was probably about 15 or 20 foot square. And then about 10 or 15 feet away, we had another one that was maybe just a couple feet thick. And then on top of that, I had some big steel beams. And on top of that, I had a tank. We were looking to see if we could use Walleye to knock down bridges.
4, 3, 2, 1, 0.
When the warhead detonated and it destroyed everything there and sent the tank through the air, people were pretty impressed, I think.
Although there's one bridge that Dave Livingston tells me that they hit it, and they hit it, and they hit it, and it would not fall down, just because of the way it was built.
By the time the operators had found something on the battlefield that Walleye 1 couldn't kill, its big brother was nearly ready to enter the fray. The big one, Walleye 2, had been in the works since Walleye 1 went into combat. China Lake had proposed a quick reaction development in the fall of 1967. Flight testing began during '68, and by mid-1970, technical evaluation had been initiated. Walleye 2 was a modular monster, a hard-target destroyer with the proven and updated TV Seeker on a 1-ton linear-shaped charged warhead. There was damn little that the big Walleye couldn't knock down. And it retained the combat-proven Walleye accuracy.
We had a 20-foot square steel plate that was used as a target. And the idea was to hit the middle of the plate and hit more or less near the middle. And then shot a second round at the plate. There was only one hole in the plate. But there were 2 sets of wing marks because one of them was rotated a little from the other, so we could tell both rounds had gone through the same hole, but just a slight deviation.
The new Walleye would go a lot farther, too. Larger wings on a larger airframe, mated with the larger warhead.
You could change your configuration by putting a different warhead in a different control section on the guidance unit. The guidance units were essentially the same, but there's modifications that had to be made to the control section to accommodate different aerodynamics.
Walleye was the first modular weapon system to go into production. And by the close of the conflict in Southeast Asia, Walleye 1 had been complemented by the larger Walleye 2, by extended-range versions of both, and by first-generation data links that allowed the pilot to follow the weapon from a distance, and even to change its aim point if need be. Smart bombs would help define the Vietnam War, although no other was of Walleye's caliber. The hated bullpup, relic of an earlier era, hung on for a few years, and numerous strap-on guidance schemes made dumb bombs at least smarter in limited use. The laser-guided bombs, LGBs, made their combat debut, eventually downing the Tan Hoa Bridge and helping to make smart bomb a household word. But LGBs had to be designated, whereas Walleye was truly launch and leave, or shoot and scoot or drop and dash, whatever you called it. If anything else was smart, then Walleye was brilliant.
We had the first smart bomb, and it was considered very smart. That's what the succulent sex were the smart bombers. That's the term we used.
I think that the laboratory system has always been very, very responsive in that regard to running things down and fixing things, or at least explaining them. Or all in all, I don't think that we did a good enough job in telling our story. Let's put it that, from a lab standpoint to the fleet.
We had a lot of confidence in VX-5 and China Lake that they could develop Sidewinder, and so we knew that they were interested in putting out weapons that would work for the guys in the fleet, and that were usable by the guys in the fleet.
China Lake had tried to maintain that fleet focus, even as the war in Vietnam wound down and the inevitable post-conflict drawdown deepened. Developing advanced systems and improving its proven products, in an atmosphere that increasingly stressed economy over innovation, became an increasingly difficult proposition. With China Lake competing with converter bombs and numerous versions of the Air Force's Maverick for scarce funding and headquarters patronage. The Air Force had actually started the converter bomb competition almost as soon as Walleye had hit the battlefield.
Hobo was simply the Air Force's reaction to not having Walleye shoved down their throat by the Navy.
After they saw what we were doing, they immediately started a competing development with North American Aviation at that time. I believe that was called initially Hobo, very much a Walleye copy. They didn't use Random turbines and things like that. They used a Mark 83 bomb.
Hobo was an Air Force converter bomb scheme using a poor imitation Walleye Seeker mated to a modified GP bomb, which didn't fly as well or as far as Walleye's purpose-built airframe, which delivered a GP bomb not nearly as effective as Walleye's purpose-built warhead, and which didn't really save any money in the long run. But it did help set a pattern for battlefields to come being well populated with dumb bomb strap-ons of almost every imaginable sort. Walleye's modularity, however, and its well-proven combat accuracy, made it a prime candidate for some impressive improvements. Although, given that Walleye is the only smart son of the first family of conventional freefall weapons to emerge from the atomic-enamored depths of the Cold War, it is ironic that one so-called improvement was the Air Force Seek-Bang, a 10-kiloton nuclear warheaded Walleye that briefly joined the TAC-nuke stockpile during the 1970s. A grim reminder that precision remains a virtue, even in atom bombs. A more practical application of the new technology, one at the opposite end of the attack weapon scale, was Snipe. Often described as a tiny powered Walleye, Snipe indeed began as the original Walleye 2, an unconventional weapon proposed for the unconventional warfare role. With rocket motor added, Snipe would provide precision punch to those platforms too small to carry other guided weapons, allowing even small helos and light aircraft to take on tanks and convoys, small boats, and a variety of soft installations. The best realized direct descendant of Walleye, however, was Condor. An upgraded Walleye Seeker in an evolved Walleye airframe, carrying a somewhat downsized Walleye warhead and packaged with a custom-designed rocket motor, giving it a 60-mile range, and a programmable autopilot system, making it the first modern cruise missile. At least that was the idea. It made for a devastating standoff weapon. A weapon that was the direct result of China Lake technology development efforts, and a weapon that tested extremely well against surface targets, and hard targets, and ship targets. A weapon that was being developed with significant industry involvement, and with significant friction between the lab and the contractor, as the Lake pursued different guidance schemes than did the Prime, and different data links, and different propulsion. And at the same time, the original was being pushed toward the outer edges of what the technology would support. Walleye's modularity had helped enable the China Lake team to meet the fleet's demands for bigger, farther, better standoff in relatively short order.
It does get credit as being the first modular weapon system. The concept was replaceable guidance sections, replaceable control sections, and within the guidance section, here's all these little plug-in modules. Every function in the guidance section could be replaced, improved, updated as you need to by unplugging this module and plugging in another one. And that was a unique concept.
That modularity allowed Walleye to be improved as soon as technology allowed. China Lake was pursuing a more stable platform for an advanced seeker. And the putative Walleye 3 would be able to see in the dark. And that phenomenally accurate, in-flight designatable, securely data-linked system would fly farther than ever.
We had a fairly active program going for a while, which we called WIGS, which was a Walleye Improved Guidance System. And it was vastly improved. It was something that you could really produce in quantity.
The WIGS guidance improvements, combined with other technology applications then in the works, would have made for a vastly superior Walleye 3. Not only better electronics, but better mechanicals. Less drag, too, for greater range. Even eliminating most of the test equipment that went with the original Walleye.
We had developed a powdered clutch actuator, completely electrical. No pneumatics, no gas cranes, nothing. And it used small electrical motors to operate the fins.
Successes aside, China Lake's dogged determination to advance Walleye was not well received in some headquarters circles, where cutting back and contracting out had become the directions of the day. WIGS caused trouble in the Condor program too, when China Lake pushed for an improved Condor Seeker design based on the WIGS hardware, which had been successfully lab and flight tested at the center, much to the consternation of the missile contractor.
They had a Seeker on that was kind of a Walleye clone, only they did it worse than we did. They threw up their hands and they said, okay, you guys want it. And so after the first two Condors ever flown had the original Seeker in it, and the later ones, I think there were about 12, had the Seeker that we designed.
It was more like 17, but it didn't matter in the long run. Condor was already under the gun. Even with tech eval successful, and op eval and pilot production initiated. Cost and schedule overruns, plus several test firing failures of the industry-supplied data link, combined with accusations of serious improprieties by the prime contractor, brought the program to a swift and final end. Condor, in both in-house and industry incarnation, was also seen in some quarters as a threat to the continued development of Harpoon, which was still a long way from the battlefield at the time. Interestingly, nearly 2 decades later, the requirement for a combat capability nearly identical to China Lake's Condor would come again to the fore. With Condor's sometime nemesis Harpoon as the basic platform, SLAM was born. Imaging Seeker, autopilot, and a secure data link evolved from the advanced Walleye design. Soon thereafter, in an evolution reminiscent of Condor's, SLAM was given wings and a broader spectrum seeker with better data linking to create the current combat fielded SLAM ER.
Way back at the T=0 or the Genesis, we were going to have a data link in this thing.
The China Lake automatic tracking scheme had worked out well enough from the beginning of the program to set aside the data link for later development. A basic link was pursued in parallel with the weapon, but getting the basic capability Walleye to the fleet was the priority. And few people know that the early data link was actually demonstrated to the highest levels in the summer of 1963.
We had our old milk wagon TM telemetry van, and we had a specially configured Walleye that had a data link in it that could transmit back to this milk wagon telemetry van. There was a long piece of coax run over to the reviewing stand where JFK and his cohorts were to be, and this TV monitor was set up in front, and the old A4 was airborne.
Since the guidance system is entirely passive, there is no known way to jam this weapon. We will illustrate the Walleye guidance system with a live telecast relayed from a captive Walleye in flight, so you may see on your television monitor exactly what the Walleye sees.
Lo and behold, it all worked. He even tracked the stand that Kennedy was on, flew at it, which may have caused the Secret Service some consternation, I don't know. But
The expansion of the air war in Vietnam and the lack of precision-guided munitions with which to fight it caused that link to be set aside for a time, however.
Finally, when we got some breathing room, and this was 67, late 67, we had always intended to have a data link in here because it would be a logical extension of the system.
A logical extension that would not only improve overall accuracy and crew survivability, but one that would allow the weapon to be redesignated from a distance, even flown remotely if need be, all the way to the target, while the delivery aircraft headed in the opposite direction.
At the very end of the Vietnam conflict, the active part of it, we had the data link. And that was really the driver for the data link, was they wanted to be able to refine the target selection after launch, and they wanted to be able to get out of there without jamming. Those first data links were probably good for 50, 60 miles, something like that, which was certainly good enough.
And with a joystick reminiscent of that which had piloted Azons a generation before,
with a joystick and with the gyro-stabilized system that we had, that a human being could control that with ease. It was duck soup. You could sit there with a joystick and you just move the joystick a little bit and you could track with impunity. Anybody could do it. It didn't require training. Donald Duck could do it. Anybody could do it. We could demonstrate this in the lab.
Data link could be on a buddy, although that came a little later, but yes, it could be done because SAMs were an issue in Vietnam. It was the AWW-13 that gave us a hardened data link with 300-mile range. The Phase 2 data link had approximately 200-mile range.
although the services, the field activities, and the contractors squabbled over the format, the frequency, the functionality, and the relative complexity of their data links. Those data links and their descendants would become essential to the modern integrated battlefield, where a weapon can conceivably be controlled by a wingman, by a faraway AWACS, by the battlefield bosses aboard the carrier, or even by higher authority.
The history of Walleye is pretty much the history of solid-state electronics still. As we would get new technology, we could see how to apply it to make Walleye better. In a 6-month time frame, 5 of us developed all of the electronics for the guidance and control section for what we would call Walleye 3. And we had a microprocessor-based tracker. We had all of our new stuff in the camera. We were still using a Vidicon camera. We were going to move to a CCD. Those were new at the time. And we had a new control section, still with electric actuators.
The Walleye that was evolving throughout the 1970s would acquire haze-penetrating and broader spectrum seekers that had demonstrated capabilities to see in the dark and in all but the foulest weather. By the early 80s, China Lake was applying programmable gate arrays, advanced high-density computers and video processors, and the amazing new solid-state sensors to a planned 3rd generation of Walleyes. Along the way demonstrating the first practical 8 to 14 micron uncooled IR imager. Those efforts attracted international interest and even returned some of that walleye-specific technology to the public.
We had scientists visiting us from France, from England, from Sweden, Scotland, Canada. These people were coming here to see what we had going because nobody had managed to do this before. And they were selling power electric Vidicon cameras of the panning variety commercially, and they hired us on to refine our digital processing for their commercial market.
But even without the new technology, the weapon's adaptability and flexibility proved to be remarkable. Even though Walleye had been designed as a smart bomb for a dumb airplane, it was readily adapted to the new world of highly integrated, software-driven platforms.
The early F-18's Walleye weapon went on well, and the system, the software for the weapons system itself, worked well with the Walleye. They did a good job. They built a weapon that didn't show its age nearly as badly as some of the other stuff that we had. It was still quite functional 20 years later.
Stand by for impact.
Priorities, politics, and inter-service rivalries aside,
Mark impact.
Walleye's own success, however, may have helped doom its continued development.
That was actually in our way in later years, because with 10,000 walleyes, the first 200 walleyes probably hit 190 targets. That got the job done, and you've got 9,800 walleyes left in inventory. Nobody wants to pay you to go design a new weapon.
So we've come a long ways in this, but I think the Walleye presented, in many ways, the beginning of that era that now exists.
Walleye, what did it really bring to the fleet? Well, it brought the most powerful punch you could deliver from the safest position, as a delivery pilot.
Walleye's last hurrah came in combat, as did its first. 130 walleyes of various mods, some out of ancient production runs, were launched during Operation Desert Storm in 1991. The weapon performed amazingly well, scoring bullseyes on boats, buildings, and bunkers. By the time Walleye went to the Gulf, precision had become the expectation, and the political ramifications of wrecking the wrong thing had become even more dire, as the conflict became the first to be truly fought on TV.
I hit my target. Did you? Yeah, it was real good.
Walleye's surgical precision, mission flexibility, and uniquely effective warhead, combined with the ability to fly the weapon at need from afar, made it a stellar, if largely unsung, performer in the desert.
Looking good. Roger, copy that.
The Iraqi Naval Headquarters at Qasir was the first use of Walleye in my air wing, and I think the first in the war. I'm looking for a T-shaped building with the bottom of the T sticking out toward me, and I flew it onto kind of the center point of the building. And the next day, when the F-14 flew over, all that was standing were the outer ends of the top of the T. I flew a Walleye 2 essentially into the lobby of the building with a delay, and brought the entire building down, and they canceled the strike for the next day. Again, the beauty of Walleye, to fly so precisely that we can fly it right into the revetted area and impact dead center in the building. The whole interior of the building was just completely gutted, and there was one tiny little hole through the roof.
And, as it had been a generation before, Walleye was sent in to turn out the lights.
You can see the large power lines coming into the building. We elected to fly it in and take out this substation, and you can see we're quite effective at it. Very good, clean Walleye shot, great target, precise, low collateral damage, exactly what Walleye's good at.
Walleye's penchant for precision also made it the weapon of choice for some more unusual missions, presaging, perhaps, an upcoming generation of battlefield imagers.
When I checked in as a junior officer in the DFA 195, the dam busters, just having returned from Desert Storm, One of the airplanes that I saw was a picture of a helicopter that had been stenciled beneath the pilot's name there. And the story behind that was even more interesting.
I was preparing to lead a 6 or 8 plane strike against a communications building on the north end of Basra about 4 weeks into the war. The intel guys came in and they said, we have intelligence that there's a Super Freelon helicopter loaded with Exocet missiles, and they said, we want you to change your strike and go after this target. And that helicopter was holding our entire battle group 100 miles further away than they could have been, and the threat of that helicopter. So the next day, I asked to be loaded with a Walleye 1, and my wingman was loaded as well. I went in, it was in fact still there, and I released my Walleye, turned away, and controlled it myself into the helicopter. And when I brought the video back, that night we moved the ships up closer to Kuwait.
You know that when that weapon hits the target, that building, that structure that once stood there is going to be razed to the ground. That's what Walleye brings to the table. It brings a major can of whoop ass.
It was used very effectively, and a few of them were sold overseas. The Israelis bought some. They used them at even longer range than the American forces used them.
And I'm told that they used it to attack Saddam's nuclear plant.
It was the beginning of what we've got to today. And look at the cost savings, and not only in terms of material, but people. Say, I want that bridge in the middle of the night, and you can go out and send one airplane and one weapon and virtually guarantee you're going to get it. That was the beginning of what you're seeing now in the smart era of weaponry.
One of the most visible of the legacies of the Walleye Condor clan is several generations of video data link pods. Looked at as something of a luxury when introduced, the data link is an omnipresent essential of the modern battlefield. Introduced late in the Vietnam War and significantly refined thereafter, by Desert Storm, the data link had become a powerful multi-purpose tool.
We never looked at Walleye as a standalone weapon. It was always going to be a data link, in-flight, adjustable weapon. The data link provided a couple things for us, not only updating the aim point, but also bringing back the video. And in Desert Storm, that turned out to be huge.
There it is right there. Hold it there. Yeah. That's it.
With Walleye and its data link, post-strike BDA, battle damage assessment data, could be taken with the follow-on strike.
Take the Walleye and fly it in after a strike with conventional weapons. Gather BDA, fly the Walleye into whatever portion of the target remained intact. The value of that BDA turned out to be huge, and I think that was one of the reasons that the data link caught on so much, and maybe led to a recognition of the intelligence value of gaining seeker data back through data link.
It's not just a single weapon in an aircraft, it's an orchestra of assets and sensors that are all integrated in a time sync, and they're able to share megabits of information, being able to coordinate which sensor is going to be guiding which weapon, and all of this being done from cockpits, or could be, whoever's on a different platform that just happens to be in on the net. Could be a surface ship, could maybe be a submarine with an antenna strung out over the water. Who knows? But if you're dialed in on the data link, not only can you move images, you can move time-sensitive information necessary to execute our mission.
It changed the way we look at air combat. I applaud all the follow-ons, but Walleye was king. There's no question about it. Walleye was king for many years. There's definitely a legacy.
Although Walleye left the battlefield to the new generation of precision munitions after Desert Storm, sometimes it does take an old soldier a long time to fade away. The pioneering technology of television guidance that Walleye provided to Maverick, to Slam and Slammer, and to generations of converter bombs in numerous guises, is only its most obvious legacy. The technology developed by China Lake for a night-capable walleye evolved into today's uncooled focal plane array imaging infrared systems. The Navy data link of the 1970s, Walleye's data link, provided the technological and operational foundation for the development of those universal data links tying together today's complex combat arena. Walleye's robust airframe was also resurrected to serve as a flying testbed for fiber optic data link experiments at China Lake. And as a tactical target for ship defense improvement projects. The hunter becoming the hunted, but still serving the fleet, even in its final days. Even as the last of the walleye improvement efforts ebbed during the late 1980s, other groups at China Lake, eager to exploit the advantages of imaging, were applying the latest technology to the pursuit of precision in the air, at sea, and in the dark, and using a solid-state CCD to create the original imaging Sidewinder, the canceled AIM-9R.
It was kind of the second generation imaging EO system at China Lake, and it went and took the basic concept that Walleye put in a package about this big around and about that thick, and shrunk it down to something that was this big around and about that long.
The evolution of the technologies supporting TV guidance has been rapid. As vacuum tubes gave way to transistors, so Vidicons gave way to solid-state multispectral imagers, practically impervious to launch shock and high-G maneuver and environmental extreme.
You see this transition over the years from glass-based things that cared about how you handled them, to smaller ones, to transistors, to integrated circuits, to highly integrated circuits, which we're using in Spike, that really don't care if you wrap them on the table a little bit or if you make them a little too cold. When you turn the power on, you don't have to wait for 30 seconds to see them warm up. You turn the power on, boy, they just come on. And it's really quite a remarkable transition in not all that many years, basically one generation.
A single generation of designers, perhaps. But as the walleye that made its name in Southeast Asia was several generations of technology removed from Weary Willie and its locked-down vacuum tube wonder weapon seeker, so the Spike that makes its combat debut will represent several generations of technological evolution beyond the transistor and the Vidicon. And it will represent significant evolution in tactics and targets since Walleye's heyday, launched from almost anything to pick out and pick off a pinpoint particular threat, or to provide the final line of defense against small but highly deadly remotes. Those little boats, and the jet skis and mini pickups and panel trucks, and those potentially guided by a new generation of kamikaze.
So we said, what's the least you can possibly have and still be effective against this class of targets? The answer is, if you can hit them, you can kill them all with 5 pounds, of which maybe a pound of it is a warhead. And what is China Lake really good at doing? Hitting targets. That's what we do.
The story of guided missiles is a story of farther and faster, more technological, more accurate, more deadly. It's often a story of bigger and bigger, as the converter-bomb behemoths of the battlespace attest. They and their data links are the result of the same pursuit of precision that produced Walleye in the first place. But Walleye's legacy, in some ways, follows the opposite course. Through snipe all the way to Spike, to take that highly reliable and highly survivable shot off the wing of the lightest attack aircraft, or off the shoulder of the sneaking SEAL, while maintaining the astounding ability to target with certainty a particular window in a power plant complex, or a particular window in a moving mini-truck. And, as you may well have a tiny TV camera in that tiny telephone in your pocket, that Marine may well have what amounts to a tiny powered walleye in his backpack, or on that tiny toy airplane buzzing about overhead, leaving the bad guys with no place to go, pursued by precision.
This was not a good place to fly through in an F-18. So why even fly through it? Why not drive up around it and deliver a walleye and let it fly through it, gliding along very quietly, arriving without any notice of it even being there, because the airplanes are 30, 40, 50 miles away. And so the bad guys, the only thing they know is if they be looking up in the sky, the moment before it comes down, then it's over.